This is Algebra 2 at Trig, working on 3A.3. This is essentially section 8.3. We're going to be graphing more rational functions. We're going to be using graphing calculators to help us graph these versions of rational equations. We're looking at a crazy looking rational equation. This is a polynomial on top with a polynomial on bottom. There's so many parts to it because every part of the polynomial with a decreasing exponent, you can tell, and a coefficient in front of each term. We have a dot, dot, dot that represents that the polynomial could be of any size. If this was a 4, a 3, a 2, and a 1, you wouldn't need any dots. But if this was a 7, a 6, you need the 5, the 4, the 3. This is really the 1, and then no exponent on your last term. So we have x-intercepts. Think about what it means for x-intercepts to happen. What is happening on a graph for you to have x-intercepts? Your graph is going to have to hit y equals 0. And for a fraction to hit y equals 0, the numerator has to be 0. That's how you find your x-intercepts. Set the numerator to 0. The graph has vertical asymptote for wherever an x value that can't exist. And that's when we look at the denominator. So we're going to have vertical asymptote at the 0 of q of x. Whatever the denominator's polynomial is where the asymptote will be for the vertical form. Now we're going to look at the horizontal asymptotes. There's a couple different options that we have going here. We've discussed these earlier. If you look at your polynomial up here, we have an m representing the exponent. And in the denominator, we have an n. So if the numerator's exponent is smaller than the denominator's exponent, what is our horizontal asymptote? Will be at 0 because the bottom's going to grow faster than the top. What if the exponents are the same? What if the m is equal to the n? What are we going to look at? The leading coefficients. And we look here, and the leading coefficients are a over b. And the situation that we're not going to discuss here is if the numerator of the top is larger than the numerator of the degree of the denominator. The degree of the top is larger than the degree of the bottom. We're not going to look at that because it would have no horizontal asymptote. It would be a slanted asymptote. You'll deal with that in pre-calc. So we're going to slide down here. We could use the same skills that we've used in the past. If you were not going to use a graphing calculator, you would need to calculate out your table. We're going to talk about using a graphing calculator so we can observe what these more complicated looking graphs are going to be like. What is our vertical asymptote going to be for this graph? How do we determine that? Look back at your notes. The vertical asymptote is when we set the 0 to the denominator. So we go to your denominator, and you're going to set it equal to 0. So we subtract 1 to the other side. And when you take the square root of both sides, you get the square root of -1, which you should realize that is plus or minus I. So what does that tell us? There is no vertical asymptote. So we have none. there is no restriction to what x values you can plug in. So before you do any of these calculations, you already know the domain is all real numbers. There is no limitation to what x value you can plug in. You can't get 0 in the denominator. The horizontal asymptote, how do we determine that? If the degrees were the same, we'd look at the leading coefficients. But in this case, the degree of the top is x to the 0 power. There is no x there. So that's the same thing as x to the 0 power. Down here we have x to the 2 power. So the m, which would be the degree of the top, is smaller than the degree of the bottom. So we know that our horizontal asymptote is going to be at 0. We are never going to reach 0. And we label that on our graph. So we're still not ready to figure out the range yet. So we're going to take our graphing calculator. At this point, we would just start plugging in points. But we're going to use the graphing calculator to help us determine those points. So we're going to go to y equals. We'll type in our numerator using -5. I would suggest to put that in parentheses so we get the habit of always having parentheses for the numerator divided by parentheses for the denominator. This is not an appropriate use on previous lessons. We're just using this on the most complex rational equations. First time I've ever relied purely on a graphing calculator to do these. So it's just as easy to type in numbers. Just takes a little bit more time, that's for sure. So you could look at your graph and you really notice that you have a different type of graph going on. We can go to our table to help us determine what numbers we should use while we're plugging in our values. So in the middle of our graph, we're going to plug in 0 for the x. And that's going to be at -5. You could see that in your graph. When we go to 1 or -1, you notice that those are both going to be -2.5. Two or -2 are both going to be -1. And at 3 and -3, they're both at -0.5. So if you needed just to plug numbers in, you could easily plug those in and create the exact same values. But we're using a graphing calculator to help expedite some of that information. So we're going to plug in our points. At 0, we're down at -5. At 1, we're at -2.5. At -1, we're at 2.5. At 2, we're at -1. At -2, we're at -1. At 3, we're at -0.5. And at -3, we're at -0.5. And you see that we're coming back up. We're approaching, some would say that we're hugging the horizontal asymptote. So how do we determine our range now? Our range is as low as -5, but it does not reach 0. So our y values are greater than or equal to -5, but it goes all the way up, but does not include 0. The other notation we could use would be interval notation, with -5 with the square bracket, because it can include -5, and a round bracket on 0, because it'll never reach the 0. Always remember to write your equation. Come down to our next one. To find out your vertical asymptote, we set the denominator to 0. So we know the vertical asymptote is going to be x equals -4. We can come in here and plot that out at -4. We can look at the horizontal asymptote. How do we determine what the horizontal asymptote is going to be? The horizontal asymptote has to do with the m and the n. It has to do with the exponents. So what relationship do your exponents have? This would be considered x to the 0 power. So the numerator is smaller than the denominator. So it's going to be y equals 0. Right now it's difficult for us to say, probably not. We could probably say that the domain is all real numbers except the asymptote, x equals -4, and the range is going to be all real numbers except the asymptote, which is y equals 0. We'll graph it and then I'll do that part. So again, this one we wouldn't need a graphing calculator for. It matches exactly what we've done in the past. But since we're practicing the graphing calculator right now, we'll go ahead and use our graphing calculator. Parentheses -8 divided by x plus 4. And when we go to our graph, we see this one get graphed out. And in our table, we can pick our numbers. We're going to either side of -4. Notice -4 has an error for the y, because that's where the vertical asymptote would occur. You cannot have a y value when x is -4. So that's why we get the error. At -5, we're at 8. At -6, we're at 4. And at -8, we're at 2. Going the other way, at -3, we're at -8. At -2, we're at -4. And at 0, we're at -2. So we're going to plot these points. We go to -5, up to 8, -6, up to 4, and -8, up to 2. So we know our branch of our hyperbola is going to be right there. Now remember, we could use symmetry to determine these other points. You could go to this new origin where the two asymptotes cross, and you could count over 1 to the left and up 1, 2, 3, 4, 5, 6, 7, 8. So now we're going to go 1 to the right and down 1, 2, 3, 4, 5, 6, 7, 8. And that's going to be the point -3, -8. You can do it either way. From this new origin, you count over 2, up 4. So now we can go over 2, down 4. You might prefer that type of way to come up with your points rather than plugging values in if you were doing this by hand. This would be an appropriate question to do completely by hand. No graphing calculator. And then 0, -2. So we would approach that asymptote and this one. And our graph is -8 over x plus 4. So you can see the domain, what x values you're plugging in. Like we said before, all real numbers except where the asymptote is. X equals -4. All real numbers except y equals 0 is the range. All right, now we actually get into the two that would really be beneficial to use a graphing calculator. If you take a look, these start to get a little bit more creative. Not required. Never used graphing calculators in the past, but we're trying them here. For our vertical asymptote, we are setting the denominator equal to 0. So that gives us x squared equals 4. So x is going to be plus or minus 2. Look at that. We have two vertical asymptotes. We have one at -2. We have another one at +2. So we label our points, our asymptotes, on your graph, -2 and 2. Looking at your horizontal asymptote, what determines our horizontal asymptote? When we look at the degrees, we see that m and n are equal to each other. So we're going to use the leading coefficients. The numerator and denominator are 1 divided by 1, so this is y equals 1. So next what we're going to do is go to our graphing calculator. I'm going to clear mine out, so second plus 712. So when I go to equals, y equals, I don't have any equations in there. Really important here, you've got to put parentheses around your numerator and around the denominator. Need those for your graphing calculator. It won't work out. X squared minus 9 divided by x squared minus 4. So when we graph that out, you can see the creative graph that is produced. So we're going to go to table. We're going to go to the 2, which has the error. That's your vertical asymptote. So now we're going to look at our points that are to the right of that. So at 3, we're at 0. At 4, we're at 0.58. At 5, we're at 0.76. You could spread it out a little bit more than that if you wished. Now we're going to look in between the two vertical asymptotes. So in the middle would be 0, that's halfway in between. 1 and -1 on either side. So we're at 2.25 and 2.66. 2.66. So we saw in the graph what's happening there. We saw in the graph that it's curving back up. It looks like a parabola. It's not exactly a parabola there in the middle. It just kind of looks like one. And then on the other side of the asymptote, it's going to be the same pattern of points. We get our 0, 0.58, and 0.76. So we can come over to our graph now and try to plug those values onto our graph. At 0, we're up 2 1/4. At 1, we're at 2.6. -1, we're up at 2.6. So this is approaching that direction. On the other side of the asymptote, we're at 0 for 3, 0.58 for 4, and 0.76. We didn't have much room to stretch that out farther. And on the other side, again, we're at 0, 0.58, 0.76. And it's good for you to write your equation, x squared minus 9, x squared minus 4. Look at where the graph crossed the x-axis. Where did the graph cross the x-axis? How could we have known that by looking at our equation? What are the x-intercepts? The zeros of the numerator. So if you added 9 and took the square root, you'd get plus or minus 3 when y is 0. Okay, those would have been your x-intercepts, where y is 0. So we have vertical asymptotes at x equals plus or minus 2. So in terms of a domain, we can plug all real numbers except x equals plus or minus 2. The horizontal asymptote is y equals 1. But what are we going to call a range? This range is a little complicated. You can either focus on where the graph is, or you can focus on where the graph isn't. Is it all real numbers except? And you would do your exception and you would cross out this portion of the graph where it's not. Or you can talk about where the graph is. It's kind of up to you. So we've got y is less than 1. And y is greater than and equal to 2.25. So that is your range. Those are the answers that we're getting. You could possibly say all real numbers except the y values that are greater than and including 1, because we don't want these to happen. We don't want 1. We don't want anything that goes up to 2.25. But it exists at 2.25. This is the exception. This is where it doesn't exist. So you've got two different versions of your range you could write. Here we can look and we notice our vertical asymptote is where the denominator equals 0. So that's going to be -3 and +3. We know we have a horizontal asymptote at y equals 2 because the degrees are the same, so we use the leading coefficients. We know our zeros of the function are going to happen at 0, so I expect to have a point at 0, because that's what makes the numerator 0, the fraction. So now I'm going to go to my table, clear out my y1, type in 2x squared divided by x squared minus 9, and you can see the creative graph that is being produced in this case. So we're going to look at our table. At 0, we're going to be at 0, of course. At 1, we're going to be at -1/4. At -1, we're going to be at -1/4. At -4, we're going to be at 4.6 almost. At -5, we're going to be at 3.1. And at -6, we're going to be at 2.6 or 2.7. On the other side of our asymptote, at 4, we're going to be at 4.6. At 5, we're going to be at 3.1, and at 6, we're going to be at 2.7. So we can graph those points out. 0, 0, 1 and 1/4, so we know that we're curving down towards our asymptotes. At 4, we're up at 4 and a 6, 3.1. And same thing on this side. So you know you have your vertical asymptotes at x equals ±3, horizontal asymptote at y equals 2, all real numbers except x equals ±3, and all real numbers except y equals 2.